Hardware-accelerated global illumination by image space photon mapping. Here's a demonstration of our algorithm. It's rendering in real time with no latency as I move the light sources in the scene and as I move the objects. Notice the color bleeding, contact shadows, and reflected illumination. The objects in this scene all have different scattering functions. The white box is diffuse, the cow is glossy, and the glass ball is both shiny and transmissive according to a Fresnel term. Because we compute global illumination using rasterization, that ball is actually a polygon mesh. Here's how the algorithm works. We start with a black screen and then add illumination from different sources. Using the same viewpoint as a shadow map, we compute the first bounce photons from the light source. These represent direct illumination, which we compute in the normal way, but we save those original photons. Then we compute the second bounce of those photons on the CPU using a ray tracer. These bounces become the indirect illumination. We rasterize a photon volume in 3D around each of those sparse samples, which interpolates to compute the radiance everywhere. Here's the final image again. Now let's look at a more complicated scene. This is a bird's eye view of a video game level. All of the illumination you're seeing is computed by ISPM. Because everything is visible, we can only run at 2 frames per second out here. But once inside the map, the frame rate increases to 15 frames per second, because we only need to compute illumination that is relatively close to the viewer. Unlike normal visible set culling, we must consider light that can bounce around corners, so this isn't exactly the same as traditional potentially visible set. This alien in the middle of the room is the Onos character model from the in-production game Natural Selection 2. If we turn off our global illumination, here's what we'd see with only direct illumination. Adding a constant ambient term loses the interactions in the scene. And here's our indirect illumination again. Adding direct illumination back gives the full model. The red light is coming from a white emitter bouncing off a red wall. To demonstrate this, I'm going to turn on slightly better visible set culling to get up to 20 frames per second, and then pull the camera back and start playing with the lights. Watch how the indirect illumination changes color while I rotate the light. Now I'll show you what the light sees. These are 2 channels of a bounce map. One is showing the surface normal, the other is showing the power of first bounce photons computed by rasterization. This is like the first bounce of a ray tracer or a photon mapper, but computed on the GPU. Okay, now let's pull the camera back and really move the lights around and see how the dynamic illumination changes. Notice the indirect illumination change in color. There are enough photons in the scene that I don't see variance even in the dark areas. Everything changes smoothly. We can move objects as well as lights, of course. Here's the wireframe for this scene, and here are the photons that are being used to compute the radiance estimate. Now I'm going to switch to another scene to demonstrate a limitation in the parameters of our model. This is the 2009 Ironworks level from Quake Live. I'm banging this red Camaro around the scene in order to create obvious indirect illumination. Notice how when the camera zooms close to the illumination, it fades out just before the surface is clipped by the near plane. Although it looks like a contact shadow from the camera, it's really an artifact of the photon volumes being clipped. Now I'll vary the photon parameters to show what happens if the kernel size is too small. I'm using the same number of photons, but now the kernel is so small that you can see the individual ones. When I increase the kernel size, they blend together and you get smooth illumination again. In closing, I give you caustics from a ring, a glass bunny in a Cornell box, and the sponza atrium with a yellow banner.